Hello everyone. So in today's lecture we are going to study a very important task in data mining. But first let's talk a bit about unsupervised learning. So in data mining we have three main concepts. So we have supervised learning, we have unsupervised learning, and we have semi-supervised. So, supervised was a concept we were studying in the previous sessions and lectures. So, it basically refers to a classification and regression. So, it means that we have data and we also have the outcome of each instance. And the outcome could be either nominal or numerical. If we have a nominal outcome, we are talking in terms of classification, while if we have a numerical outcome, we are talking in terms of regression, very likely. Besides, we have unsupervised learning. So basically, in unsupervised learning, we only have the instances. So we don't have the answers or the responses or the outcomes there. So this is the main difference. And in between, we have semi-supervised classification. So it means that we have some instances which are attached to the decision classes, and we have other instances that we don't have decision classes or numerical values. So we don't have the outcomes, okay? So it's a mixed problem. But in this course, we are going to study supervised classification. Actually, we already did it. And in this lecture, we are going to talk about unsupervised classification, the first task dedicated to unsupervised classification. So, semi-supervised classification, I wanted to mention it, but we are not going to cover it in this course. So, in summary, so we have a data set, and the question we need to ask ourselves is whether we have labels or the outcomes, yes or not. So if we have the outcomes, we can talk in terms of classification or regression because we have a supervised problem. If we don't have the labels, then we are talking in terms of unsupervised classification. So we have two main tasks. We have association and we have clustering. In this lecture, we are going to cover clustering, while association mining is something we are going to discuss extensively in the next lectures. However, this is quite important here. So we should understand that the learning concept depends on the data we have and also the purpose. Okay? So of course, if we don't have the right data, we probably cannot do some specific task. For example, if the data we have is unsupervised by nature, it will be really difficult to perform classification or regression, for example. Okay, so this is the data component. But at the same time, we need to take into consideration the purpose. So what we want to do with the data, even if we can do it. So this is the main difference between data and purpose. So in summary, data refer, the data we have, the pieces of data we have, refer to the thing we can do. So the resources we have in order to perform some task, while the purpose refers to the thing we want to do, even if we have the data to do it, okay? This is very important when it comes to data mining. So, in summary, we can say that unsupervised data mining algorithms should be able to infer patterns from the data set we have without reference to the outcomes or just the decisions, okay? So the outcomes refer to the decision classes, for example, in the classification problem or the dependent variables in regression, just for us to have a clear view about the different concepts we can associate to unsupervised and also supervised classification. So in the case of unsupervised learning and more specifically clustering, which is this lecture about, the problem we want to solve here is that we have several pieces of data or instances, and we want to discover clusters or just groups of instances. And this is how the problem looks like. So here we have a problem, let's say, and we have two dimensions. So we have the first dimension and the second dimension, which are basically the variables describing the problem. And here we can see clearly that we have three main groups. And this is something we can do it by visual inspection, because this is something that we can handle ourselves. I mean, the space of two dimensions, okay? But of course, this is not always the case. Now let's go a bit deeper into this problem. I mean, in the problem of clustering objects, let's say, and let's talk a bit about this particular example, which refers to the document analysis. So let's suppose that we have 10 academic papers and we want to cluster them according to the topics they are addressing. So we have 10 papers, those are the instances we have. So we apply a clustering algorithm, and later on we are going to obtain, in this example, three groups. The first group refers to the papers of computer vision. The second group contains the papers related with text mining, while the third group contains the papers related with neural networks. Okay, of course, in this example, we have the documents, and the documents are the instances, and we need to describe the documents. And the way we have to do it is by using variables, right? So, but my point here is that we have a lot of applications that in the case of data mining, to which clustering is actually quite useful. And in this example, as you can see, we don't have a decision class. So we have groups, and those groups actually have a meaning, which is, in this case, computer vision, text mining, and neural networks, but they are not necessarily the classes, the decision classes in a classification problem, okay? So, as a matter of summary, we have three main types of clustering algorithms. So we have CRISP methods, we have fuzzy methods, and we have hierarchical methods, okay? And we are going to discuss a bit the main features in each case. So let's start with the k-means algorithm, which is probably the most important representative of CRISP clustering. So the goal of the k-means algorithm is to minimize the sum of distances between the points and their cluster centroid. So we have a cluster centroid, which is basically the representative of each group. And again, the goal here is to discover the groups. And the way that the k-means algorithm does that is by minimizing the distance between the different instances or objects, or yes, minimizing that distance with respect to each representative in each group. Okay, so we are going to see how this process goes in detail. So one thing that we need to determine in advance is the number of clusters, which is the k parameter. Okay, this is something that we need to define ourselves. So in this particular example, the first step, as I was mentioning, was to detect the number of clusters. Not to detect, to specify the number of clusters. Is how many clusters or groups we want to obtain. The second step is we need to select or define some random points, which are the initial centroids. Okay, this is something that it is done randomly, so we don't need to perform any fancy procedure here because this is the initial point for the algorithm to start working. Okay, so later on we are going to assign each point, I mean each instance or each object to the closest cluster centroid. And remember that the centroids in the first step were selected randomly. Okay, so in that way, if we have two groups, we are going to have two cluster centers or centroids. And yes, the next step, the step number 3, is to assign each point to the corresponding centroids. And to do so, we are going to use the minimal distance. So the distance is the indicator here, how to do so. So later on, we need to recompute the centroids. So we have two groups, right? Those groups were formed in the step number 3, and later we need to recompute the centroids because in the first step the centroids were randomly determined, and now we need to recompute it. We need to update them. And the way we have to do so is by aggregating the components or the objects belonging to each group. This is one way. Or the second way could be just selecting the most important or the representative of each cluster. This is the two ways, the most popular ways of recomputing the centroids. And later on, we just repeat step 3 and also the step 4 in that order. Okay, so the procedure goes on, and later on, we are going to stop the algorithm. But of course, we need to discuss some stopping criteria for the algorithm. So here we can see some examples. The first one is the centroids of the new groups don't change anymore. So every time that we are recomputing the centroids, we are obtaining the same centroids over and over again. So it doesn't make any sense in computing more iterations or performing more iterations. The second criterion is whether the points remain in the same cluster. So if we see that perhaps the centroids are changing a bit, however, the clusters don't change in the sense that the clusters contain the same objects, so there is no reason to keep going anymore. So we can stop the algorithm. And the last criterion is actually that we reached a maximum number of iterations. So we just set up in advance a maximum number of iterations, and if those iterations are reached, we just stop the algorithm. So it means that the clusters were changing a bit, the clusters, the centers were changing a bit as well. However, we need just to stop. And the way we have to do so is by establishing this parameter. Okay, so in summary, we have 3 main stopping criteria. So now we are going to discuss briefly an example how this goes. So in the first step, so this is the data we have here, right? So we are going to take k equal to 3. So later on we can discuss how to set up k, but for the time being we are going to set up this parameter as k equal to 3. Excellent. So the first step is we need to randomly assign the centroids. So basically we just compute the initial centroids. So in the second step, we just assign each data point to the closest centroid. So in that way, we are actually forming the groups, okay? Later on, we just move the centroids to the average location, which is basically the center of each group. And in this step, the thing we are doing is that we are recomputing, we are updating the centroids, okay? And later on, we repeat steps 2 and 3 and so on until a stopping criterion is reached, okay? This is how it goes, and this is the way we have to form the clusters. Now I will introduce another clustering algorithm that belongs to the second group. So it's the Fuzzy-Simmons algorithm. So this is an example of fuzzy clustering. So, but first, why do we need the Fuzzy-Simmons algorithm? Well, one reason is because in the k-means, the clusters or the objects, they can belong to a single group, only to a single group. And this is an example of the bivalent logic, right? So you can only belong to a single set. And this is not the best way probably of representing data. Why? Because sometimes the clusters or the groups, they overlap each other and we should be able to capture that behavior, okay? And this is something that we cannot do with k-means. But first, it would be nice, before introducing the Fuzzy-Simmons, it would be nice if we can introduce the very basic principles behind the fuzzy set. So here we have two different paradigms. So we have the classic logic versus the fuzzy logic. So in the classic logic or the bivalent logic, as I was saying, one object can belong to only to a single set. So one object cannot belong to different sets at the same time. Let's take, for example, the temperature. Whether you have fever or not. So here we have the set strong fever. And for sure, if you have 40 degrees, it's a clear indicator that you have a strong fever. But here you can see in this diagram, okay, here, that 39.3 is in the boundary. And 37 here is outside the set strong fever, and 38 is in the boundary, and 38.7 is in the boundary as well. So if we are going to take, for example, let's say 39 degrees, the 39 degrees is the threshold, is the boundary we are going to establish and say, okay, the fever, the temperature is belonging to the strong fever set or not. But 38, for example, 0.7, probably it can be considered a strong fever as well. So my point here is that we have a binary set. If temperature is inside that set, we can say for sure that the fever is going to be strong. But if it doesn't fulfill the condition, the temperature is not going to be placed inside the strong fever set, although it can be quite similar to the components inside the set. And this is something very difficult because the next question is, which is the most suitable threshold, or which is the most suitable boundary we can draw in this problem, okay? And this is not so easy because it depends on the problem, because this is just the strong fever temperature, but we can model similar problems using that approach. So in order to solve that problem, Professor Lofty Sadeh introduced the fuzzy logic. So in the fuzzy logic, the principle is quite simple, and it says that one object can belong to different sets at the same time. But with different membership degrees. So here we have the concept of membership degree, and this is something which is basically the key in fuzzy logic. Okay, so just to make my explanation a bit more visual, this is how the bivalent logic looks like. So we have a cat here, a grumpy cat, and for sure there is no hesitation, this is a cat, and here this is a dog. So we have a clear boundary in this example. So this is how the classic logic looks like. But at the same time, we have a situation like this one. So you can see here a very cute puppy, but actually it has some features that remind us a cat. So it's not so easy to say the puppy is a cat. For sure, it's not a cat, but it has some features that are similar to the features of cats. Okay, and this is how the fuzzy logic looks like. And we can say, okay, for sure it's a dog, but at the same time, it has some features that remind us a cat. And this is what we feel when modeling problems using fuzzy logic. Now, back to the fuzzy C-means algorithm. So, each group has a membership function that returns a number in the interval 0, 1. So, this is quite important. So, membership values or membership functions produce values in the 0, 1 interval. And the way we have to understand those values is by analyzing the membership of each object to the different sets. And in this example, the sets are just the groups, okay? So now we are getting again into the clustering problem. So in summary, we can say that the membership value indicates how much this instance or the object belongs to the cluster. And this is the basic principle behind the fuzzy C-means algorithm. Now we need to introduce some math here, but we are going to go through the different components to see how this math is important and why this function is important when computing the fuzzy C-means algorithm. So the purpose of this algorithm is to minimize this error function or the cost function. This is something we want to make it really small, and we are going to see why. So, but first we need to understand the main components, or the first component we have here is M, so capital M. So it denotes the number of data points in the data set we are going to use in order to discover the clusters. Okay. So the second component is C. It's actually a parameter we need to define in advance. So C here is equivalent to the K parameter in the K-means algorithm. Okay, so basically it's how many fuzzy clusters are we going to compute, okay, with the fuzzy C-means algorithm. And again, this is a parameter we need to specify ourselves in advance, okay? Later on, we have this very important variable, let's say, and this is the membership degree. But the way we have to read it is, okay, this is the membership degree of the data point I to the fuzzy cluster J. So it belongs, I mean, whether the extent actually to which the point belongs to the cluster, okay? This is very important. And this is a value that needs to be in the 0-1 interval because it's a membership degree. Later on, we have M, so a small m. M is the fusification coefficient, and this is also a parameter we need to define ourselves in advance, but in that sense, we have not many choices because the literature says that m equal to 2 is a suitable or probably the best way to configure this parameter. Okay, so in summary, we can set up m equal to 2. Later on, we have V, and basically V denotes the prototype. So the prototype in fuzzy-C-means is equivalent to the centroid in the K-means algorithm, okay? And we are going to see an equation in the next slides, how to compute those prototypes. By the way, those prototypes are quite important, and again, we are going to discuss it why. And finally, we have set, and it denotes a data point to be clustered. Okay, this is one data point belonging to the training set, I mean, to the data set we have. Okay, so those are the components we have in this cost function. And the thing we want is to minimize this cost function. And why do we need to minimize that function? It's so simple, because we want each point to be allocated to a prototype, which is in the end the way we have to form the clusters, but taking into consideration the membership degrees. Okay, this is the trick here. The last two equations I would like to introduce to you are, the first one is how to compute the membership degrees, and secondly, the prototypes. Okay, this is something that we can perform quite easily. So perhaps the equations look a bit I don't know, complex, but they are not, because in the end, we have all possible components we need in order to perform that calculation here. So you can see here that we have the coefficient, we have the prototypes, we have the data points. C is something that we know in advance, and this is something that we can implement quite easily in Python, for example, or R. Excellent. So this is the equation related to the membership values. And here we have the equation associated with the prototypes. So this is the way we have to compute the prototypes. So the representative of each group. This is what a prototype means. And here you can see that we perform this weighted sum here, and we just perform a normalization here just to make the numbers more representative, I mean, so we can obtain better prototypes. Okay, now the thing we need to ask ourselves is, what is the meaning of those prototypes? And it's so simple. If we have a data set and we want to compute the clusters, perhaps the clusters or the groups are not the ultimate information we want to get it from the data set. Perhaps we want to build prototypes so we can describe the whole data set with fewer points, which are basically the prototypes, the representatives of the data set, the massive, let's say data set we have. Okay, and this is the reason why fuzzy-C-means is so important in data mining. In summary, because it allows computing the clusters, the groups, but also it allows computing the prototypes, which is the way we have to synthesize or summarize the data. Okay. So now I will introduce the hierarchical clustering, which is basically the third approach we are going to briefly mention in this lecture. But again, the question is, why do we need hierarchical clustering? Okay, because we already know k-means, and we have also fuzzy-C-means, just in case we want to obtain the prototypes and discover overlapped patterns in the data. Okay, well, in the case of hierarchical clustering, the problem with k-means and fuzzy c-means is that we need to set up the parameters in advance, the parameter k and also the parameter c in the second case. But this is something that is not required when building hierarchical clusters or just when running hierarchical clustering algorithms. Okay, so in summary, we are going to use hierarchical clusters when we don't want to set up ourselves in advance the number of groups, and we are going to see why. So this is how the results of a hierarchical clustering looks like. So this is the structure of the algorithm. So what the algorithm produces. So the thing is, how can we understand this structure here? Okay, it's so simple. It depends on the thresholds, and the threshold is basically the line we are going to draw in order to obtain the groups we want to. So if we want to obtain two groups and to conduct the analysis using two groups, this is something we can do. So we just draw the line here. But if we want to obtain three groups in order to perform a more detailed analysis, for example, the only thing we need to do is after the algorithm is completely performed and is done, we can just obtain different configurations. And the way we have to do that is just changing the line. And in this example, you are seeing here, we have three groups, but if we go a bit deeper, we can build four groups and so on. So basically, we don't need to run the algorithm again. So we have a single structure, and later we can obtain different cluster configurations just by changing the threshold. Okay, this is one of the main reasons why hierarchical clustering is so powerful. Okay, so please allow me to make a brief summary of the different paradigms we were discussing. So first, we have CRISP clustering, and in CRISP clustering, the thing we are obtaining are disjoint groups. So we don't have any overlap between the groups, okay? And in those algorithms, like for example, k-means, we need to set up in advance the parameter k. I mean the number of groups. At the same time, we have fuzzy clustering. Again, the parameter c must be given, and the only difference here, which by the way is a very strong difference, is that fuzzy clustering allows computing overlapping in the data. So the groups we are going to produce, they can be overlapped. And this is something which is more realistic, let's say, because in the end, the data sets and the groups, they are likely to be overlapped. And this is something we need to take into consideration. And finally, we have the hierarchical clustering, and the difference here is that we don't need to set up in advance any parameter concerning the number of groups we want to obtain. This is something important. So again, we can obtain different group configurations, but we don't need to run the algorithm again. So this is something that we perform after the clustering is actually done. Okay, this is the summary. Here is worth mentioning the distance function, because we were talking about how to form the groups, whether a point was closest to a centroid and so on. But of course, we need a distance function. And basically, the distance function says the difference between two objects. So if we want to measure how dissimilar two objects are, we use a distance function to do that. So basically, it provides a numerical quantification on the dissimilarity between two data points. So the extent to which two data points are different. Okay. And of course, we have different functions, and of course, the results can change according to the design function we used to obtain the groups. So here, I'm not going to get into detail because this is something that we were mentioning in the previous lectures, but the only thing you need to know is that we have different approaches and different distance functions. This is something I wanted to mention, but besides, please take into consideration that sometimes we have data containing both numerical and nominal attributes. So we should be able to select the design function fulfilling those features. Okay, so being able to handle both nominal and numerical features at the same time. So this is the main message I wanted to convey here. And finally, I wanted to discuss some evaluation measures, because in the previous lectures we were talking about evaluation measures in the case of supervised classification, like for example in regression or classification. But here in the unsupervised setting, and more specifically in the clustering task, we need different evaluation measures. And here we have two main evaluation measures. Of course, there are many in the literature, but I wanted to introduce only two. But first, we need to discuss what we want to measure. This is something what we want, and later on, the next question is how can we measure the thing we want to measure. Okay, so back to the first question. What we want is very compact clusters, but at the same time to be very separated from each other. This is the thing we want to do. So we want very well-defined, let's say, clusters. And so in order to obtain that, we need compact clusters, small clusters, if we can afford it, and at the same time we want them to be separated. So this is the cluster structure we have, and of course this is how can we design a proper evaluation measure. So the first evaluation measure I wanted to introduce is this one that produces value between -1 and 1. So the way we have to interpret the results is as follows. So first of all, if we get 1, basically we have the perfect cluster structure, because again, the clusters are compact, so the information is compressed, and at the same time, the different clusters, they are separated from each other. So this is the perfect setting. So if we get values around 0, it means that the clusters are indifferent. So basically, the clustering we obtain is not significant. And -1 is just something completely messed up, okay? Because it's basically that we assigned completely incorrectly the using an incorrect approach the objects. So the clustering we obtained was just a mess. And of course, those are 3 values that we can use to understand the measure. But again, the values we are going to obtain, they are between -1 and 1. Okay, so we can obtain different values. And we have a second measure. Okay, the second measure is a bit different, but in principle, we're measuring the same thing. So basically, the DOM index is measuring the ratio of the minimum of the intercluster distances and the maximum of the intracluster distances. So here we have two concepts. So we have the minimum intercluster distance, which is basically we have different distances, but they are measured for a particular cluster, okay, inside the cluster. This is the meaning of intercluster. And we have, of course, several distances. So we are going to retain the minimal distance in that setting. At the same time, we have the second concept, which is the maximum of the intra-cluster distances, and those are the distances between groups. So taking into account the centers of the different clusters we have, because again, this evaluation measure is performed after the clustering algorithm is complete. Okay, the clustering process is done. So we have the clusters or the groups, and we want to measure the quality of those groups. Okay, and after having the minimum of the intercluster distances and the maximum of the intra-cluster distances, we just compute the ratio in that way. And this ratio is just the done index, okay? But as you can see here, we have different ways, different approaches. However, the thing or the objective or the setting we want to measure is exactly the same. Is how well separated or compact the clusters are. So basically, this is the goal. So that was the lecture, the first lecture concerning unsupervised learning, but actually the lecture was about clustering. So I wanted to introduce the concept of unsupervised learning. That was the reason I decided to use this name for the lecture. But in the end, it was about clustering. And in the next lectures, I'm going to cover association mining, which is another task that belongs to unsupervised learning as well. So please read the materials and go through the slides, and we can discuss more in the Q&A session.